Well, hello everybody. It's Coach Smith here, and what we're looking at today is we're trying to understand the concept of a linear function. Okay, and you've had this before, and you've had it since middle school. So this is should just be a little quick review, and just to get you ready to deal with these things and more complicated problems. But for today, we're just going to review them, what they look like, what they can do, and a few other linear functions that you might not have remembered quite so easily, and one in particular. Okay, first let's take a look at a linear function. That's simply, if you look at the slide, it's the old slope-intercept form. Y equals mx plus b, where b is the y-intercept, and m is the slope, the number, the coefficient in front of the x. Okay, what we're going to do here is I'm just going to start off with letting the y-intercept be 0. So it's going to be y equals mx plus 0, or just y equals mx. And the easiest m, or slope, that I can think of would be 1. So here's the graph y equals x, okay? And you can see it in the background here. All right. And you get a nice slope of 1. You go over 1, you go up 1. You go over 2, you go up 2. And of course, slope is 2 over 2, which would be 1. So no matter where you are, the slope is constant. And that's what really makes a linear function linear. No matter where you check the slope, you're still going to get that 1 over 1, rise over run. And even if you take it out to like it's got a run of 4 and a rise of 4. The rise is 4, the run is 4, 4 over 4 is 1. So it has a slope of 1. Now, if you use a negative coefficient, your slope is going to flip. So if you take a look at the green line, it's sort of a mirror image. It's a reflection, if you will, of the y equals x graph. This is the graph of y equals negative x. Okay, and so there you go. All right, so it's just this one. And again, your rise is negative. Let's say you basically drop 1 for every 1 you go over. Drop 1 for every 1 you go over in the x. You drop 1 in the y for every 1 you go over in the x. And that's going to give you a negative 1 over 1. And that's just a slope of negative 1. Okay, looking back at the graph of y equals x, the good old nice and simple. It's about as simple as it gets for a linear function. Let's go ahead and see what happens if we add or subtract a number to the end of it. If we actually add or subtract a number, that's getting us back into slope-intercept form where you have that b and that y-intercept. So what let's do is let's go ahead and say y equals x subtract 3. All right, notice the blue line there. All right, there's our parent graph, y equals x, it's in green. And then we're going to adapt a little bit by subtracting 3 from it. Well, it drops it down 3. And look where your y-intercept is. It's negative 3 on the y or up and down axis. Okay. Now, if we were to add a 3, your slope-intercept would become a plus 3, and thus not only the line scoots up 3, but the y-intercept is right where you would expect it to be. Okay. All right, cool beans. Now, what I'm going to do next is I'm going to show you the graph of y equals x, linear function, y equals negative x, another linear function, but also the absolute value function, y equals the absolute value of x. Now, you're going to miss it when I click. All right, I'm going to click on y equals the absolute value of x, and you may miss it. You may have noticed that the top lines up here got a little heavier. So let me make it easier for you. I'm going to get rid of y equals negative x. I'm going to get rid of y equals positive x. And what's left is your absolute value function. The absolute value function literally takes any value of x, positive or negative. See, here's your x-axis. It's represented. This graph is above every value on the x-axis, including 0. Any number can be plugged in for x. But the y value is what you get when you take the absolute value of those numbers. And the absolute value of any number is always its positive, its distance from 0. So you may plug in a negative 7. I'm sorry, let's go down here. You may plug in a negative 3 for x, but you'll get a positive 3 for the y. So just remember the absolute value function always returns positive answers. Therefore, your graph can never dip down below the x-axis, well, unless you actually change it. So if I was to put a minus 5 here on it, then it would, of course, slide it down 5. If I were to put a minus 2, it would slide it down 2. And if I were to put a plus 1, then it would move it up 1. Okay, so you can see how that works. So just remember the absolute value by its distinctive little point at the bottom there, or the top if you were to play with the negative signs. Okay, now what happens if you actually have y equals x, and instead of having a slope of 1, you have a slope of 2. All right. So this is y equals 1x right here in blue. Let's look at what y equals 2x is, and also in blue. All right. Let's see if we can find another y equals x here. There's a y equals x there. All right. Now it's in green. All right. So we have a green y equals x. Let's look at y equals 2x in blue. All right. Let's increase that number, the coefficient in front of x, to 3. Now it's a darker purple or black. And now let's move it up to 5. Okay, so as you can see, it starts swinging closer and closer to being a vertical line as the slope increases. Okay, now remember, positive slope, if you're driving a little car, I know this is rudimentary, but hey, it works for me. If I'm going from left to right and I'm driving a car, I'm going to go uphill up this slope. Okay, if I have 3x right here, if I'm going left to right, I better put it in four-wheel drive, but I'm still going uphill. And that means I've got a positive slope. Now, if I were to have a negative slope like this one, -4 in light blue, if I'm driving my little car, I would start going downhill. Hope the brakes are good. That's a pretty steep slope. All right, and so anyway, I'm just going over a review of what the linear functions look like. Y equals mx plus b is the basic formula for it, whereas b is the y-intercept and m is the slope of the linear function. Okay, so now that we've talked about what it looks like, let's take a look at a few problems here. You'll notice my lovely Neyland Stadium background here. And I'm going to go ahead now and just pop up the drawing program I use. Function notation literally takes the y. You could say y equals 2 times the absolute value of x minus 1 plus 5. That's the blue right there. But if you want to use function notation, and that's kind of the next step up, you would just use f of x or g of x or y of x. And function notation is used when you have a lot of graphs on one piece of graph paper. So not only do you have different colors, you could color the graphs, but also if you label them like f of x for one of them, g of x for another, and maybe h of x for a third one, then when you refer to them to your students or to other people you're dealing with, they always know which one to look at. If it's all just y equals this and y equals that and y equals another graph, I mean, pretty soon, even if you're using colors, you're going to run out of ways to differentiate them or to refer back to them clearly, and function notation allows you to do that. Now, one thing you may see when they're dealing with function notation is they'll tell you to find the function value at a certain point. All right, they want this one. They want you to find the value of this function right here at f of 1. So we're going to plug a 1 in for x and figure out what that is. So let's just go ahead and do that. We're going to say that f of 1 is equal to this function with the 1 placed in where the x is. So it's 2 times the absolute value of 1 minus 1 plus 5, which is equal to 2 times the absolute value of 0. 2 times the absolute value of 0 will be 2 times 0, and that would be 0 plus 5, or 5. The function value at 1 is equal to 5. All right, I'm running out of room here, so I may just only do the second one. I'm not sure I have room to do the third one, but you'll see the point here. If I'm going to find the function value at 3, what I'm going to do is I'm going to take a 3 and I'm going to plug it in for the x in the functiony part, the right side of the function there, where it has all the interesting things. So I'm going to have 2 times the absolute value of 3 minus 1. And then after I do that and multiply, I'll have to add 5, because don't forget there's a plus 5 out there. So you work from the inside out. 3 minus 1 is 2. Okay. So it's 2 times the absolute value of 2 plus 5. Now the absolute value of 2 just also happens to be 2. So you get 2 times 2, which is 4, plus 5. And in this case, 4 plus 5 is 9. All right, and so the function value at 3 equals 9. All right. So anyway, there's just a couple of examples of using function notation and finding specific values at certain x values you're plugging into the function. Go ahead and close this out. Work your problem set for today, and please, please, please make sure you're turning things in through Google Classroom. Again, I have lost my little off button here. It got when I switched screens, it kind of went away. So I may have to click a million times to get this thing to pop back up, the little control panel. But, anyway, nice weather we're having. Yeah, I tell you, it's been a little hot, but still not too bad. Cool in the evenings and in the mornings, and definitely looking forward to winter. Boy, I'm clicking away over here. I promise you I am. And this little off button's there it goes. It's just popped up. So anyway, you guys have a great day, and we will catch you next lesson.